Everyone to this week's version of our International Inverse Problems seminar. So we are happy here to have Yimin Zhong from Duke, previously UCI, to talk about quantitative photoacoustic tomography with simplified PN approximation. So we are excited to hear about what this is, Yimin. So welcome and thanks for giving a talk.
All right, thanks. Okay, thanks for the invitation for this seminar. So this time is my second time to give the talk at this seminar, and today I'm going to talk about the quantitative photoacoustic tomography with the so-called simplified PN approximation for the radio transport model. This is a joint work with Hong. So this is an outline of this talk. So first, I'm going to quickly give a review on the photoacoustic tomography. Then we introduce about this simplified PN approximation, which is a simplified model for this radio transport equation. Then we combine them to study this photoacoustic tomography and show some result about that. Okay, so first, the introduction about photoacoustic tomography. So basically, in biomedical imaging, there are two kinds of prevailing modalities that people use for those imaging techniques. The first one I would like to say is the optics-based this optical-based tomography methods, such as the optical tomography, fluorescence, optical tomography. So all of these, they use the laser source to probe the underlying medium, like the tissue. So you inject this laser into this tissue and you collect the information outgoing from this tissue's boundary, and then you use this information to identify what's going on underneath. So this is the basic model, and the objective is to use this the optical modality to find out the underlying structure of the biological tissue, like tumor tissue, like tumor cells in the tissue. This kind of doing this kind of detection. And the reason that we can do this is due to the optical property of different tissue will have quite different optical properties. So in here we have I have included a figure about that. So if you look at about 1,000 nanometer wavelengths, so if you use about the infrared laser to probe the medium, you will see that the red line here and the blue line, these two lines are most important lines. So the blue line, the red line, they have a relatively large difference. And the red line here, they refer to the absorption coefficient or absorption property of the oxygen blood. So that means the blood has more oxygen. And for the blue line, that is the absorption coefficient for the blood without sufficient oxygen. And they have a quite large difference because the y-axis, the vertical axis actually is in the log scale. So actually they have a very large difference. And because of this kind of difference, you can identify what kind of cells are like tumor, what cells are healthy, because the tumors grows faster, so it will consume more oxygen. So in the tumor cell region, the oxygen level is relatively low, and the healthier cells will have a relatively higher oxygen level. So in that way, you can differentiate this kind of properties. So that's why the optical tomography can work in that region. And there's only one limitation of this optical-based method, that is the image will have relatively low resolution. So even though you can have the you can see there are some you can identify the roughly the region where the absorption coefficient is smaller than in other places, but you cannot identify precisely the resolution is very low. It's just like about 1 or 2 mean-free paths. So it's not that satisfactory if you are just using optics alone. So that's for about optics. And the second modality that I want to introduce is the ultrasound based. So this is also a popular modality people use for biomedical imaging. And the basic experiment are just to use the ultrasound. You probe this ultrasound into this medium, and then you connect the ultrasound information as outgoing. And the reason to use that is the ultrasound usually has quite short wavelengths, so you can have a relatively high resolution. And if the medium is not that scattering, but also it has the limitation when the intrinsic limitation when the medium is highly scattering, like the skull. So in the LDAS scale, there are many porous, and the porous small structure in the skull, then it has strong scaling. So that will impose difficulty for the imaging. But the limitation of this ultrasound-based imaging method for human bodies is that because most biological tissues are water-based, so the wave speed are relatively like a constant. So you won't see very large contrast. So so even though you have a very high resolution image, but there's a very little information contained in the image. So that is the problem. So nowadays, people are trying to combine these two kind of modalities to which is so-called the hybrid imaging. So like in the optics, we have this high contrast from the optical properties, and from the ultrasound we can have the relatively high resolution. So people are trying to combine these two things to produce the image with a high contrast and also high resolution. And two of these representative modalities I want to introduce is the PhotoAcoustic tomography, and another one is the ultrasound modulated optical tomography. And today we will focus on the PhotoAcoustic tomography. So what is the PhotoAcoustic tomography? So here I have included illustration about the underlying physics about the PhotoAcoustic tomography. So suppose you have this tissue placed in this domain, and the tissue is this pink region with some kind of underlying structure, the green part, the gray part, and this black dot, maybe some kind of structures you are interested in. And the experiment are performed like the following. So you inject this near-infrared laser into this medium. And also you put this ultrasound transducer, which is just some kind of like a sensor around this medium. And then when the near-infrared laser, this kind of laser photons propagate into this medium, you will get scattered and also get absorbed. And when the photons get absorbed by the medium, it will get heated because the energy, because of this photon energy, get absorbed. And this part of energy will eventually lead to a thermoelastic expansion. And this expansion will consume this part of energy, and soon the temperature gets cooled down. And this expansion and contraction will propagate ultrasound. So this process is very quick, and this ultrasound will propagate through this medium and eventually captured by the ultrasound transducer. So this will be the experiment, and you can see in this experiment the two processes are involved. One is this physical process is related to the near-infrared laser propagation. So laser photons were propagated into the medium. And the second process getting involved is the ultrasound. So after this medium absorbs this energy, you will trigger this ultrasound, and ultrasound will also propagate into the medium and eventually captured by the sensors around. And usually, in the physics, these two processes should occur at the same time, but the laser lasers travel at light speed, but ultrasound travels at a lot of scales slower. When we write the physical models, we can view these two processes separated. So that is the compromise here. So here is a workflow for the PhotoAcoustic tomography. So we have already introduced the first a few blocks, like the thermal expansion, the thermoelastic expansion trigger the pressure field and the propagate ultrasound, and we measure this ultrasound data at the boundary. And when we are trying to do the reconstruction, we have usually we have two steps. First, we get this. We recover the acoustic process, then recover the optical process. And about the photon transport process here, there are actually so in the old days, people are trying to use the diffusion process to simulate this physical process. Like regarding this, the tissue is highly scattering, and usually this kind of approximation gets unsatisfactory results. And so nowadays, more and more researchers are trying to adapt these transport models to get a more precise physics for this process, since the tissue is relatively small. And for the ultrasound process, usually people are trying to use the acoustic model, but for some medium like the bones, there are also elastic models getting involved. Okay, so first we focus on the photon transport process. So we regard the true model as that's a transport model, and we use this rate of transport equation to simulate this photon transport process. So this is the rate of transport equation. So this U stands for the photon density function at the location X and the travel along the direction of V. So basically, the phase space is involves this the spatial location and also the travel direction. And for this equation, on the left-hand side, it stands for the transport part. Basically, the left-hand side stands for the transport operator for the direction of V, and on the right-hand side, it stands for the scattering component. The scattering component that in the V direction. And this P function is a scattering phase function, stands for the scattering, stands for the probability function that the photons get scattered, travel from a V prime direction, get scattered into V direction. And the coefficient sigma A and sigma S, this stands for the scattering coefficient and absorption coefficient. You can regard that as a probability that the photon particle, what's the probability that the photon particle gets scattered at the location X, and what is the probability that the photon particle get absorbed at location X. And on the boundary, we use this F, depends on both X and V, to stand for the laser source. So the boundary gamma negative stands for the incoming boundary set. That is the travel direction is pointing inside this medium. And for the scattering phase function for biomedical tissues, people usually use this so-called the Henry-Greenstein function to simulate this physical process, which is a function here. And the G is the anisotropy. So for typical tissues, the G is relatively large, close to 1. Okay, so this is a physical process about the photon transport. And to simulate, so as we have mentioned, so the part of the energy absorbed by the medium will trigger this ultrasound. So to simulate this, the energy absorbed by the medium, we use this the following quantity to simulate this process. So sigma A is the absorption, and the integral of this photon density. So the purple part here stands for the total photons stands for the total photons gathered at location X in all direction. And the sigma A stands for the absorption. So sigma A times this integral quantity is the total absorption, the total energy absorbed at the location X. And the epsilon, this coefficient, is the so-called Grunesian coefficient, representing the efficiency transforming from the photon energy to the thermoelastic expansion's initial pressure field. So, so after you multiply this Grunesian coefficient, you will get the initial pressure triggered from this so-called photon acoustic effect. That is the used to propagate the ultrasound. So H you can regard it as the initial pressure field. And after we have this H, we can propagate this ultrasound. So here we just, for simplicity, we use this acoustic model to give a rough introduction about this process. So basically, we have this acoustic model with some wave speed field, and with this initial pressure field and initial velocity field. And after you solve this acoustic wave equation, the ultrasound will propagate in the whole domain. So in the physical space, and the measurements are taken on the boundary of this domain, and for the whole time. So basically, you will have this pressure field on the location, on all the location on the boundary, and also all the time. And regarding about this reconstruction process, as we have mentioned, their typical reconstruction consists of two steps. The first step is to reconstruct this acoustic step. That is to recover this initial pressure field from the ultrasound signal. So basically, you have this ultrasound signal measured on the boundary, and we try to find out the initial pressure field for this ultrasound field. And this step usually assume this wave field is known, and the reconstruction will be quite stable if you back propagate all the signal into this medium with this known wave speed, for example, like the constant wave speed. But if the wave speed is unknown, then small perturbation in the wave speed will trigger quite a large distortion in the reconstruction. So there's very famous result by Playman and Gonder that shows that there's no positive stability, positive sublevel stability for this kind of process. And for the second step, so after we have reconstructed this initial pressure field, now we can try to reconstruct the quantities of interest, like the absorption coefficient, scattering coefficient, and the epsilon, the Grunesian coefficient, from this initial pressure field, using this using the formula that this quantity is the product of this Grunesian coefficient times the photon density, the photon energy. So with the transport model, this process is less studied, but for diffusion process, this problem has been fully solved. So here I just want to mention a few results from the transport model. So the first result is from Guillaume, that if the full map, which is like this D2M map, here is just the albedo operator. The albedo type operator that is given all kinds of laser sources, and you measure all kinds of the initial pressure field, then you can recover any two coefficient of these three if the third one is known. So it doesn't say anything about whether or not we can reconstruct all of these three coefficients simultaneously, but we know that if one of these three coefficients is known, then we can recover the other two. But we don't know if there is a gauge transform there to give you an equivalent class or not. And if we are given one single source, Then in the non-scattering case, or weak scattering case, the absorption coefficient can be reconstructed if the coordination coefficient and the scalar coefficient are known. So this is just a probability argument, and you can show that this process will give you some kind of like Lipschitz stability in general. However, if you want to reconstruct all three or reconstruct at least two of them, given the third one is known with only finite number of laser sources, there's no results at all. So this problem actually is an open question, and whether or not we can use a finite number of sources to do the reconstruction if I want to know, say, two out of these three coefficients. Say. And there are many numerical results already showing that this is seem to be true, that the theory actually is still absent. So, so from the above, so from the previous discussion, so we already have some kind of insight about this problem. So if we push the result to the diffusion limit, we already know that the previous result is already very sharp. That is, if we know two, if we want, we cannot reconstruct all of these three coefficients. We can only do two of them if the third one is known. This is exactly true for diffusion model, and in transport model, this is also true if we are given the full map, but we don't know whether or not that's true for finite many of sources. Okay, so if that is not possible, then in practice, we already in practice like biomedical imaging experiments, we already know that the scattering coefficient does not change too much for a local tissue. Then usually we just assume the scattering coefficient is some kind of constant, and we focus on the other two. So this is something that we can do for in practice. And in the following, we try to limit to one extreme case, that is the laser sources are isotropic. It does not depend on the angular variable. So we restricted ourselves to this kind of laser sources. So because this kind of laser sources are more, I would say it's the worst case, because that does not have does not give you any angular dependence. And we try to study the problem with this kind of source, and with just a finite number of sources. We try to study this the PhotoAcoustic problem and with this kind of setting. So, like I have introduced in the very beginning. So in order to start this, we combine with the previous PhotoAcoustic model with this simplified P approximation. So what is the simplified P approximation? So this approximation is just the approximation for solving the radial transport model. So here, to derive this simplified P approximation, actually is quite simple. So in the quickest way is to study this the one-dimensional radial transport model, which is the planar geometry. You can also say this is like the slab geometry. The median is like a huge slab. So or the layer median. The model can be regarded as a one dimension in the physical space, and the boundary condition becomes just just two constant on the boundary, which is the angular independent. So after we have put everything in one dimension, then we take the Legendre polynomial expansion of the solution in terms of the angular variable, in terms of this Legendre polynomial, and we truncate this Legendre polynomial to the nth mode, and then the previous planar geometry radial transport model will become this kind of coupled ODE. And if we want to solve this ODE, of course, you have a infinite dimension if we have this n goes to infinity. even you want to solve this n for a finite expansion, this is still impossible. So in order to solve this, we need to close this system. So one way to do that, we just truncate this moment to show that, to say that the -1 and n+1 are all zeros. Then you got to close the system, and the coefficient of the sigma n is just a combination of this absorption coefficient and the scattering coefficient regarding to a multiplier that are related to the anisotropy parameter with regard from this Henry-Griston model. So after we have this ODE model, we can also observe that if we represent this UN in terms of the another two, and then put back into the same model, we can eliminate all the order moments, and we only have this even order moments. So this is just some trick to reduce this the first order equations into a second order elliptic equations. And there are some boundary conditions for this kind of model, but the boundary conditions are just integrating this boundary source function with regarding this to the Legendre polynomials, and you will get this the boundary condition look like a Robin boundary condition. Okay, so to derive this simplified approximation, this is just some crazy operation that just one more step, which is quite crazy. It's just to replace this differential operator in one dimension with this Laplace operator with this gradient, and also replace the boundary condition with this Neumann boundary condition operator. Then you will arrive at this simplified PL model in 3 dimensions. And for this model, okay, and for this model, what I want to say is that even though this kind of transform is crazy, but it's not definitely wrong. It's not necessary to be wrong. And you can prove that for layer median, this is definitely true, right? Because this differential operator, it will be exactly like this gradient operator for layer median. And you can also show that for piecewise constant coefficient, these two models actually give you the same result for the 0th order moment, and that is the key for our approximation to be working, because if this simplified PL model is, if that is correct compared to the true model, just matching this U0 moment, then you can see that because our photoacoustic process only involve this angular average, which is 0th model, then we got everything we need. However, even though everything is seems so nice, there are still some limitation for this kind of simplified model. So first thing is that you can see that the simplified PL model involves just roughly half n equations, because we have reduced all the number moments. We only leave this even number moments. So you roughly have half n equations. But if you focus on the PL approximation, which is basically you build the equations for the spherical harmonics moments, which are all transport models, then you will have roughly half n squared equations, and these equations are hyperbolic. So you can see the difference between these two. And the PL model, of course, will converge to the true solution. But for SPN, it is not known for what kind of case to derive a precise criteria to show SPN model is approaching to the true model. We can only show that the simplified PL model is equivalent to the PL model when the coefficient are piecewise constant locally, and for the slab geometry, the layer median, or infinite geometry, if the total the total absorption coefficient is constant. For these three cases, we already know that the results are true. So these two models are equivalent, and we know the PN model converges to the true model. So that means in these three cases, the simplified PN model are a good model. We'll give you a good model to simulate the radial transport model. But for other cases, we don't know whether or not the simplified PN model gives you a good one or not. So in general, you can use a numerical result to show that these two models are different. Even in the limits, they could be different. And what is worse is that for some cases, the STPN model, when n is large, could give you a worse result than the diffusion approximation. So that is the some drawback in this model if this median behaves really bad. Okay, so now we try to combine the simplified model, simplified PN model with the photoacoustic tomography, by replacing the radial transfer equation with this the SPM equation system. Then you can. So after you take this the change of variable, that is take this kind of combination of this Zhong moment, then you can derive this decoupled system for the new variable with this additional term here. That is this Sn will be the nth row of the inverse of this matrix, and this matrix is just an up triangle matrix. This is just a kind of like a nasty formulation, but it will be used later in the analysis. So this system where we can show that coupled with this boundary condition, which is a very large Robin boundary condition, coupled with this kind of boundary condition, you can show with this initial pressure formulated with these new variables, we can put everything into this the weak form. We just take the test function to the coupled system and follow the standard ways that we do for the elliptic system to derive this weak form. And we have this bilinear formulation with this the stiff matrix and the mass matrix, and also on the boundary you get this the boundary integral terms. And then you can show that all the matrix here, all the operators here involved are positive, especially this boundary integral is the positive matrix. Give you this kind of like the positive. And I use this the standard analysis next to Milgram theorem, and also the Sobolev inequality. You can show this bilinear form is bounded and also strictly cursive, which shows the problem formulated in the SPM model is very close. So you can have the unique you can have the unique weak solution for this SPM model. So that means that we can try to study this solution. And to do the reconstruction, assuming that we know that the problem has to assuming this the problem permits this kind of unique weak solution, we still need some more assumptions. The first assumption we take for the reconstruction is that the absorption coefficient is much smaller than this quantity. So 1 minus g times sigma s, this quantity is known as the effective scattering coefficient, which means that if you want to use a diffusion model to do this to simulate this process, this is actually the coefficient that we use for the diffusion. So if this coefficient is much larger than absorption, then we can do the simulation. We can do the approximation that in the SPM model that all the coefficients sigma n can be approximated by the absorption coefficient, except the first one. In this way, we get the fully decoupled system between these two coefficients. Otherwise, you will have a coupling between this absorption and the scattering, which makes the analysis much more complicated. So after with this kind of assumption, we have proved that if we have two coefficient norm, and if we have this coordination coefficient and absorption coefficient, both are norm, and we have two sets of absorption coefficients, and suppose we have done the acoustic reconstruction part and only focus on the quantitative photoacoustic part, that is reconstruction from this initial pressure for the coefficient. We have these two sets of initial pressure. Then we can show that there's a uniqueness of this inverse problem. If the initial pressure are equal, then we will have this absorption coefficient uniquely determined. And we have the following stability estimates. That is roughly speaking, the error in the absorption multiplied with this constant will be bounded by the error in the initial pressure with this Lipschitz stability estimate. So these results, I want to emphasize that because previously I've mentioned, if these two coefficients are known, we already know that for the transport model, which is not the SPM approximation, for the transport model alone, we can show that we already can reconstruct this absorption coefficient, but only for weak scattering case, because there's a perturbative argument there. But here we can show that for any laser source, you enter the SPM model, and you can show there is a stability estimate. It does not have any requirements on the laser source. So and here this constant depends on your model and also depends on the domain. So we already so according to this, one question which is natural is that because for certain kind of setting, we already know that the SPM model will converge to the real transport model where n goes to infinity. So we might wonder, okay, now if we want to get something like stability estimate for the true real transport model, can we just extend this n to infinity? And then if this constant is bounded, then we got the stability for all the transport model. Then the answer will be very nice, right? However, this is not true. The reason is that as n grows, we will get a much larger equation system from the SPM model, and intuitively the coupling will let this will make the stability worse because of this coupling. So definitely this constant will grow, but do we have a bound for that? The answer is no. The constant will grow polynomially in terms of n, and and we can show that the growth constant is proportional to about n to the power of 11/8, up to a log factor. So it is not that bad. It's not as bad as exponential, but it's just some kind of like a Hilbert type of growth. So intuitively you can counter this part if you get some kind of faster decay in this source function. You will probably have some kind of counter. You can counter this kind of growth. And I also want to emphasize that this constant, this power is not sharp. It still can be optimized, but I didn't do that. And the analysis tool are actually quite simple. It's just a bunch of eigenvalue in-quality, and the countries in quality to estimate the eigenvalue of the boundary integral part. So we have this kind of growing constants, but it's still not that bad. It doesn't really mean that the true equation, the true relative transport equation, does not have any stability. The reason is that this constant this constant is only sharp when you have equipped with the corresponding boundary laser source. So for each n, you will have a laser source to give you this kind of a better constant. But for certain laser source, if you fix that laser source, this constant does not have this factor does not have to grow in this way. This only shows that the worst case could be like this bad, but given a boundary source function, it's not necessary to be like this bad. It could be bounded, but we don't know that yet. I haven't really looked into this case. And also, if the SPM model converges to the true model at a faster rate, which means this the difference between these two, suppose H2 is the true model solution and the H is just SPM model. If this convergence, the convergence of this between these two is decays faster than this quantity, then we will get the uniqueness result at least for the radio transport model. But still, I haven't looked into that, so it's still an open question. Okay, so another scenario, and here I want to talk about is about the reconstruction of the coordination coefficient. This case is probably the easiest one, since suppose we know the absorption coefficient and scattering coefficient, then the model is completely known. Then we can directly giving you an explicit reconstruction scheme for the coordination coefficient, and you can show this kind of stability estimate is good, and also this you can show this stability estimate is sharp, and also this C does not depend on the choice of this model parameter n. So no matter what n is, this stability is always true. And the hardest one probably is the scattering coefficient. So suppose you know this absorption coefficient and a coordination coefficient, and you have two sets of these scattering coefficients, and they match on the boundary of this on the domain. Say they are constant on the boundary, and then you can show that the following stability estimates. And here, this V is a function depending on this n and x, and also a parameter lambda, which is arbitrary. And on the right hand side is the difference between these two initial pressure fields, and the norm is H2 norm. It's no longer L2 norm in the previous analysis. It's they request more on the regularity of this initial pressure field. And also, to make this inequality like a stability estimate, you will need this Vn to be positive. But this Vn function is not necessary to be positive. It is only positive for certain under certain condition. So it's not necessary. So this inequality not necessary to be a stability estimate. But the more detailed analysis for this part is really, really difficult. So here, what I want to emphasize is that in order to have a good stability estimate for this scattering coefficient, you will need some regularity estimate for this for the initial pressure field. Okay, so how about the simultaneous reconstruction? So simultaneous reconstruction, we borrow the idea from the diffusion model. So that is, if we take the ratio of two data, so suppose we have two data sets, then the coordination coefficient can be canceled and the absorption coefficient can be canceled. Then the ratio data will become something like just related to the data. So this is just a solution related to quantity. Basically, it's just the average of solution ratio with another average of solution. And using this kind of quantity, we try to reconstruct the coefficient first, then reconstruct the coordination coefficient. And this process, actually, the analysis for the analysis, we can only have some linearization analysis, and which does not provide any insight about this problem. But numerically, we have tried to use this regularized optimization scheme for this, and later we will show that the reconstruction is pretty bad because of this. Because this quantity is relative, is kind of like smoothing. So any substructure in this H1, H2, they will be smoothed out when you take the ratio. Okay, so let's show this this numerical result and try to interpret some insight from it. So here, what I did is I take this. I just take two boundary source function. In practice, like when you are using the true data or performing the true biomedical experiment, what you wish is to use a lot of boundary sources, as many as possible. But here, we just try to illustrate the data, how this numerical things work. We just use two source function. One is just a linear source function on the boundary, and another one is just a few bumps on the boundary. And these bumps are simulated by these sign functions. So you can see that you will have just a few bumps on the top, a few bumps on the bottom, and for the absorption coefficient, the scattering coefficient, and the gluonation coefficient, we just choose this fountain functions. And the gluonation coefficient, usually we don't really care too much. I just choose a very simple function simulated here, like two valleys and two bumps here. And the first experiment is to show that the SPM model is not necessary to give you the approximation to the radial transport model, which is already known, because for this coefficient, you can see they are quite complicated. They are not necessary to give you piecewise constant coefficient. And here is the result. So you can show that the error. So the numerics here are just the error between this average the radial transport model and the true the true average of the solution from the transport model. So it's just a comparison of the SPM model and the true radial transport model on the so-called radiation function, which is the average solution. So you can see for the F1 source, the SP1 approximation actually gives you the best approximation, and all the rest will have a little bit more error. And for the second source function, you can say SP7 gives you the best approximation, and the rest will give you a little bit more error. So it is just trying to show that the previous argument that the SPM is not necessary to be the true model. It will give you some error depending on the setting, but you can see this error in our experiment is not necessary to be large. So if your noise is like the 5%, then the modeling error is not sufficient. It is something that you can tolerate. And here is convergence of SPM functions. So because we don't know, so there's still no result about what is the approximation rates of the SPM model to the true radial transport model. There's no argument, not even the SPM models convergence rate. Here we just show that it's likely to be exponential convergence, but the analysis is still absent. Okay, so for the reconstruction of absorption coefficient, so here we add 5% of the multiplicative noise to data, and here are just the reconstruction error from this model. And you can see the larger error are concentrated on the boundary, right? You can see in the interior, the error is relatively small, and near the boundary, the error is relatively large. And this is because when you are using the SPM model, they are actually elliptic equations. The system is elliptic, but we already know that for the transport model, the behavior on the boundary is hyperbolic. So there's a mismatch on the boundary for the solution in terms of average. So So you can see you will have larger error near the boundary, but in the interior, the solution almost have no difference. So you can see that the reconstruction is pretty good here. But near the boundary, the errors are mostly concentrated on near the boundary because of this so-called boundary layer effect. We cannot compensate that using just the elliptic equations. And you can see the error is just around this noise level because the model does not provide too much error from this true model. And regarding the scattering coefficient, it's a little bit different because as I have shown that for the reconstruction of these absorption coefficients, the stability involves this H2 norm. So you have to enforce some kind of regularity to give you some kind of stable reconstruction. So, but if you just add some manipulative noise to the data, this H2 norm is not bounded, right? Because it's the random noise will amplify this kind of noise, the noise. So what we do is to take the Fourier transform and add the noise in the Fourier space. Then you will preserve this noise level. However, this kind of way adding noise is pretty bad in practice because it not only perturb this high frequency information, it also disturb this low frequency information. So you will expect that the data is going to give you all kinds of perturbation in the reconstruction in different frequencies. And for the reconstruction, we use this numerical optimization way to do that. And we added this regularization. And here, normally people use this L2 norm to minimize the discrepancy between these two data sets, the simulated data and the true data. And here, because we have this kind of requirement of the H2 norm that should be bounded for the data, so we need a little bit more on this part. Ideally, we should use the H2 norm, but H2 norm meaning that for two dimension, you need the solution has to get some kind of Hilbert continuity, and if we solve that using some kind of like a finite element method, then it will be very expensive. You have to use some design, select the aggregate finite element, which is 5th order polynomial. So it's kind of like difficult to do that or more expensive. So here we take a compromise. We just take the H1 norm. So which is basically you won't have a lot of trouble when you solve this. using just a standard finite element. So here will be the results. So for the first row, it's just the first source function. The second row is for the second source function. So you can see there is a huge difference between these two source functions. And in the first row, you can still see that the reconstruction still can be seen. Here, the first column, second column, third column is just for different n equals 1, n equals 7, and n equals 17. So you can still see the reconstruction of this coefficient, the small disks can be seen, but also you have many strips, these artifacts, because we have disturbed all frequency of information. So that is something that you should expect. And I also want to say that there's a large artifact near the boundary, these two strips, especially in the 17, in the n equals 17. These two strips are exactly due to the layer the boundary layer difference, because the model there's a discrepancy between these models, and this discrepancy, this image happens exactly near the boundary. So we have this kind of artifacts very strong. And for the second row, the reason that the reconstruction is very bad is because of this so-called vanishing gradient of this initial pressure. This can be seen from the diffusion model. When you are doing the diffusion model reconstruction, you are actually solving a transport equation. the transport equation is the speed field. It actually is the gradient of this initial pressure field. And here, if this initial pressure field, this gradient has some vanishment in the median, in the middle of the median, then the gradient will vanish. Then you cannot trace back from this boundary into this median. You have to stop at, you will have almost nothing to be recovered in the median. So that's the problem. So you should choose some kind of source function to avoid this kind of phenomenon. So here, the first source avoided that, but the second source cannot avoid this. And for the simultaneous reconstruction, the results are really, really bad. Like for the simultaneous reconstruction with absorption coefficient and coordination coefficient, if you have only like a 0.1% multiplicative noise added, you still can see the fountain, and also can see some kind of underlying structure, but the resolution is pretty low, and the error is about 16%. That it's not very sensitive to the model. So basically that means the modeling error already dominates everything. It doesn't really matter what kind of model you choose. This is what you should expect. And for the reconstruction of the absorption, the scattering coefficient and coordination coefficient, and here is the result. You still can see a lot of strips due to the error due to the noise we added. And you can also, but in this case, you can see that the reconstruction is actually relatively good. It's much better than the absorption coefficient case. But again, because of the modeling error, the error actually is not very sensitive. Okay, and some conclusions. So yeah, so that is the talk, and I want to just emphasize that the original problem is still an open question, and I'm happy if you want to discuss with me about this question. That's it.
Great, thanks a lot, Yimin, for a very nice talk about many interesting aspects of this problem. So the floor is open for questions now. So please feel free to unmute yourself and ask questions.
Can you hear me okay?
Yeah.
Sorry, my internet's kind of choppy. Yimin, you mean just a general overview question about your approach here? Your approach involves no machine learning, correct?
No machine learning. No machine
Okay.
learning.
Okay.
No, the gradient, the vanishing gradient is not the
great talk.
machine
Thank you.
learning
Thank you for the
question.
talk.
Yeah, so it's basically so the talk is about the using some kind of approximation model to study this open question, provide some insights of what kind of way should be a good way to do the reconstruction. But again, if your median is a layer median, the problem actually is almost solved. So this because the SPM model is exactly true for the layer median. And if you want to push the result from layer median to the limits to the radial transport model, you just need to solve this question, whether or not the SPM model can converge faster to the true model for the layer median faster than this rate. It seems to be true if the source function is smooth enough, then probably you will have a faster convergence rate. But I don't have a clue or how to do that in a rigorous way. It's intuitive, but I don't know what is the correct way to do that. Say you have this n go to infinity, and H2 is the true data, and H1 approaching to that data faster than this quantity. Then this quantity will converge to 0. didn't got a uniqueness. But I just don't know if that is really true.
Any other questions for Yimin? So Yimin, I was just curious. So you started out with your original transport model.
Yes.
That is still an approximation. So do you have any intuition for how good in the applications the original transport model is for the phenomenon?
Yes, it's still yes. It's not necessary to be exactly true, but for a lot of applications, it already gives you something much satisfactory than diffusion model.
Yeah.
Especially for the medium that is relatively thin. So optically thin, then the transport model is already good enough to reveal this the photon behavior. If you want to get more precise phenomenon, you probably need to look at the Maxwell equation. Then you won't get anything. At least we don't know for what kind of randomness regime we should look at. So for now, the photon model combined with biomedical imaging problems is already a very nice combination. And for many applications, I would say it's already pretty good. Give you good approximation. Actually, I think that's already good. But here, what I want to emphasize is more mathematical, not from application-wise. It's just whether or not this kind of average data can give you reconstruction.
Good. That was very nice. If there are no more questions, let's thank Yimin again for this very interesting discussion regarding an important image problem. Thanks for joining us today.